today is Harry Train. Harry introduced edge exchangeability in the context of network models, and probably today is going to take us to dynamic networks.
Okay, thank you. Okay, thanks a lot. Thanks to the organizers again for inviting me, and thanks to you for sticking it out to the end today. Glad to be here. It's the theme of this program has been very close to my interest in networks. There's two general foundational questions that I've been interested in networks over the past several years, and I had the opportunity to discuss some of that work. One of the questions was in modeling heterogeneous structure in data, things like sparsity and power law, so I had the opportunity to present that back in July. That was work that I've done on edge exchangeability with Walter Dempsey. Today I'm talking about work on dynamic networks, so this is a situation that a lot of the talks have been in which we observe, or the data that I'm thinking about is some collection or sequence of graphs that evolve or that changes over time. Okay, so there's some fixed population or sample of vertices. Those are fixed, and what changes over time is are the connections or the edges between them. Okay. So as Eric mentioned, this is an area that is getting a lot of attention, even within the past several years. So I started thinking about this, I think, around 2013, but a lot has happened since then. Just to give an illustration of the kind of model that I might be thinking about here, although I won't talk about any specific models, and I won't talk about the exponential random graph model or the temporal exponential random graph model very much after these first two pages. But this is an example of a Markov chain model on the space of graphs. So this particular transition probabilities are described as an exponential family. So we have the conditional distribution of the graph at time t plus 1, given where we are at time t, depends, is given by this exponential form with some parameter and some sufficient statistic that depends on the present state as well as the next state in the Markov chain. Okay, so this is one of the perhaps more well-known models out there in the statistical literature. Pavel Krivitsky has worked a lot on this, and Mark Hancock and several others. There's several other types of dynamic network models. This is certainly not an exhaustive list. I apologize for that, but the field is moving relatively quickly at this point. So what I'm interested in is in understanding what might be good models in this setting. So good in the sense that there's certain natural or implicit statistical assumptions that come up in this situation often. So this is the data that I'm thinking about. I have this, and I'm going to model it according to a Markov chain. And so I should say that I'll be talking today about both discrete and continuous time processes. Although for the first half or so, most of the illustrations will be in discrete time. And I'll also be in the situation where I'm assuming an infinite population of vertices, the natural numbers, and the population process is a Markov chain on the space of infinite graphs, such that it satisfies two conditions. So it's a Markov chain in time, but it has an exchangeability condition in terms of how the transition probabilities work. So all that means is that if this were my data, the assumption is that these labels that are assigned to the vertices, they don't carry additional information except to identify the same individual across time. So once I fix this vertex or this individual at time 0, this is a consistent labeling in the sense that it's the same element, but aside from that, the specific choice of 2 or 1 or whatever wouldn't change. So exchangeability is in terms of the transition behavior. So if I were to relabel the process jointly at all times, I would preserve the structure, and so the distribution of that would not change. So that's the first assumption.
So that implies that your graph is dense.
It would imply that, which yes. Well, assuming I have an exchangeable initial state and then an exchangeable transition probability, then marginally at each time, then I have an exchangeable random graph, and it would be a dense graph. And the second assumption, and this is kind of an implicit assumption in a lot of in a statistical setting. I'm assuming that the process that I observe, or the data that I observe, is a sample, right? So if I have a large population or an infinite population, hypothetically, I'll only observe the process for a finite sample of vertices. And when I fit the data, if I fit a Markov chain to that data, I'm making a stronger assumption, which is that the Markov property for the population process projects down to every sample that I could take. So in this case, if I were to subsample these vertices and look at just the process on those 4 vertices, then that would also obey a Markov chain. Okay, so we saw the idea of projectivity come up in Christian and Jennifer's talks, and this is a notion of projectivity, but in the setting of Markov chains. Okay. So these are the two assumptions that I'm working with, and these are two, whether they're natural assumptions or implicit assumptions, they do come up. And going back to the example from the beginning, the temporal exponential random graph model, the idea of exchangeability, the property of exchangeability can be incorporated, and typically would be, I believe, although I haven't worked with these very much in myself, but that could be incorporated just by making the sufficient statistic invariant with respect to a joint relabeling of the pair of graphs that we're dealing with. So when I put a superscript sigma, that's just the graph G relabeled by according to sigma, okay, the permutation sigma. But it's been well known for a little while now that these temporal or exponential random graph models in general don't have this projective property. And that certainly wouldn't be the case in the temporal extension either, unless the sufficient statistics has a rather strong property. So that was shown. The conditions under which that hold was shown by Shalizi and Rinaldo several years ago. So the question that I'm interested in here is what if these assumptions of exchangeability and projectivity are desirable? What do those assumptions or what do those properties in what way does that constrain the model that we're working with? In what way does that constrain the process? Okay, so I'm interested in the transition, in describing the transition behavior first and foremost. Okay. So we've heard a little bit about exchangeable random graphs here, and we've heard about the Aldous-Hoover theorem, and I'll just talk about this one aspect of it. Which is that, okay, a random graph is exchangeable, or a random graph, if the distribution assigns equal probability to any 2 graphs that are isomorphic up to relabeling. And so if the vertex set is countable, then the Aldous-Hoover theorem describes the distribution characterizes the distribution in terms of some function f. This is a non-unique function. But it says that we can generate a copy of our random graph by evaluating this function at IID random arguments. Okay, so these are IID uniform random arguments. And the consequence of this, so this is a key part of one of the proofs, or the main proof of the theorem that I'll talk about, several of the theorems I'll talk about. But there's also a nice qualitative interpretation that this decomposition gives, and I'll come back to this later. In statistical terms, we get a decomposition in terms of an overall global effect. So this is a random effect that is common to all edges in the graph. Okay, so this is analogous. This is exactly the same as picking a graphon at random, for example. So that was mentioned yesterday. And then to each vertex, there's a random effect. So there's an effect that only comes into play for edges involving a given vertex, and then for each edge there's yet another independent random edge effect. So that's just a composition, or just really something that's a consequence of this exchangeability property, as we'll see a bit later. Okay. Okay. So in the situation we're in here, I'm interested in discussing or characterizing the behavior of these Markov chains. So I have to get a handle on the transition behavior, the transition probability. So when I'm at time t going to time t plus 1, I condition on the state at time t. So conditional on where I'm at time t, the distribution at time t plus 1 is not exchangeable, but rather we'll have a certain type of relative exchangeability property, which is that the combination of the exchangeability and the projectivity properties. So what that adds up to is what I call relative exchangeability, and this is work this work was later extended beyond the setting of graphs. This is work I've done with Henry Tausner, and I might be able to mention some of that at the end if I have time. But the idea is that by the exchangeability of the transition behavior and the projectivity properties, what that amounts to is if we're conditioning on this graph at time t, so this is a fixed, treat this as fixed, treat this as random, so this is the conditional, this is generated from the transition probability conditional being in state g, then what that amounts to is that if we look at every subgraph in our random graph gamma, so I'm writing gamma for the graph at time t plus 1, then the marginal distribution of the subgraph is invariant with respect to the automorphisms of the corresponding subgraph at the previous time. So in this example, if I were to permute 4 and 6 in this graph, I don't change the structure. And so I can permute 4 and 6, that doesn't change this structure, and so it doesn't change the distribution of this subgraph, the marginal distribution of this subgraph. And so that's a stronger assumption. Notice that's a stronger assumption than saying that this graph the distribution is invariant with respect to all automorphisms of this whole population graph here, because you'll notice that if I were to swap 4 and 6, when I do that, that doesn't preserve the structure up here. Okay, so that is a stronger condition, but this, in some sense, feels more natural in statistical applications as well, because, again, we are typically in a situation where we're observing this sampled data, and so we're only really able to say things or to condition on things that we've observed moving into the future. Okay. Okay. So under these assumptions, and with that definition of relative exchangeability, what I can get is an extension of a simple extension of the Aldous-Hoover theorem and some kind of minimal extension, in the sense that we have a function, so the distribution gamma, subject to some conditions on this graph G. Okay, and can talk about that later if you're interested in those. But really, for the purposes of these Markov models, the conditions are satisfied. Then there's a function which now takes 5 arguments. We have the random arguments just as before. And when we generate the graph at the next time, what we have to do is take into consideration the structure of the graph at the previous time. And what this says is that the only bit of information we have to take into account when determining edge ij at the next time is what's going on at edge ij at the previous time. So that's a very local kind of structure. And this is, it turns out that this is not always, so Henry and I worked on a generic theory for relative exchangeability where these don't have to be graphs. And that this type of nice local dependence will not always be the case. But it's a consequence of kind of the nice structure of the space of graphs, that we only have to look locally to generate these.
So what
these
are
things.
the kinds of other structures for which this nice local property would not hold? Just missing.
Would not hold. Partition. Okay. Okay. So this is a theorem not about the Markov chain at all. It's treating G as fixed, gamma as random, but in our Markov chain setting, we're conditioning on the current state. So this comes up, and this helps us in describing the transition behavior. And here's how. suppose we have a random graph, gamma. It's relatively exchangeable with respect to G, so it has this representation. Now ignore where this came from. In other words, ignore the underlying structure G, but from this function, little g here, we can generate a pair of graphs. Okay, so I generate a pair of graphs which is jointly exchangeable in that I can jointly relabel them both according to any permutation. I don't change the distribution. And what they are is, to generate W0, I evaluate these at random arguments, just as in the Aldous-Hoover case, but I just fix the first argument. W1, I fix the first argument at 1, and I evaluate at the same randomness, the same random variables. And so that gives me a pair of graphs. And what this does then is I can use this as a random operator, and this is maybe, depending on how you think about these things, this could be a bit bizarre, but this actually turns out to work pretty well, and it actually characterizes how these things work, which is that once I have this pair of graphs, I'm thinking about it as a function or an operation, a transition operation from going from time t to t plus 1. And what happens is, so W0 corresponds to no edge, W1 corresponds to an edge, and so what I'm going to do is, this is my graph at time t. To generate where I go at time t plus 1, I look at each pair of vertices, and I either look in W0 or W1, depending on whether there's an edge between I and j and g, and then I copy. Okay, so in this case, there's an edge between 1 and 2, so I look in W1 because there's an edge, and then there was an edge in here, and so I just copy the status in that case. Between 1 and 3, there's no edge, so I would pick from W0. There's no edge there, so there's no edge in my random graph gamma. There's an edge between 2 and 3, so I look in W1. There's an edge, so I copy it down. And so the next state is obtained by piecing together these two graphs according to the structure of this graph G. And by the construction, this will be relatively exchangeable with respect to whatever this is. And notice that although these were originally generated as a result of this function, which was somehow might have been related to this underlying structure G, I can run any graph through this operation, right? And so now I want to use this idea or this operation to describe how these Markov chains evolve. Okay.
But the little g depends on the big G, right?
Yeah, in this case it does. Yeah. So we're not at the case where. So I want to somehow get rid of that dependence. Right? That's what you're getting at. Yeah. So let's try that. So just let me state the theorem first, which is. It turns out that we can do this. In other words, for any Markov chain with our conditions, so exchangeable and projective, there exists a probability measure on the space of 0, 1 by 0, 1 valued arrays or pairs of graphs. So these are the these W's, such that the way that we generate the Markov chain is at each time, to go to the next time, we pick an IID copy from omega and we run the current state through that operation. So there's an IID sequence of these operators according to omega, and we just continue to iterate this procedure. So in other words, when we're generating the transition out of time t, when we generate the bit of randomness, it doesn't depend on the current state. But the distribution at the next state does depend on the current state because we're evaluating that random operator at the present state. Okay, so this is what it looks like at each time. We have a graph, we pick a new one, IID copy from this characteristic measure, we put it through this operation and we come up with the next graph and then we repeat. Okay, so it's a pretty simple description. And I'll go through. So I guess I'll discuss a little bit of the idea behind the proof, especially there's some curiosity maybe about that. But it's not very long, this description, but this is somehow a key idea to how we can get a description in terms of a measure which doesn't depend on the current state of the process. So the idea is that I need to generate a G that is somehow representative of the whole state space. Okay, and so in some way this isn't so far removed, although this is just an analogy. This isn't exactly a direct correspondence. If you think about a Lévy process or Brownian motion, in some way you can describe the behavior of a Lévy process, which has stationary independent increments, for example, just by how it behaves coming out of the origin. Okay, and this is that we don't quite have an origin in this example or in this case, but we can generate a random version of it, or we can generate some representative element of the state space, study the transition behavior out of that, and we're good to go. So the way that we do that, what I'm going to do is I'm going to generate my G first randomly according to, I can choose a lot of distributions, but for simplicity I just pick an Erdos-Renyi distribution with parameter 1/2, could be any parameter P. So that gives me a random graph G, and it's exchangeable. Okay, so it has an Aldous-Hoover representation, and more than that, it has a very simple Aldous-Hoover representation because I only have to worry about this last piece, which means that all the edges are IID. Okay, and so that actually does turn out to be important, and that's also why some things don't work and some things do, because we can't always do that. And then given G, I'm going to generate a random graph gamma from the transition probability of the Markov chain. So now I have a pair of graphs, G and gamma. G was generated from the Erdos-Renyi, gamma from an exchangeable transition probability, so jointly these have an Aldous-Hoover representation. And the key point and the reason why the Erdos-Renyi was important, for one, it has a simple Aldous-Hoover representation, and for two, every finite graph embeds into it. So it's a universal object, and it contains every finite graph with probability 1, right? And so if I want to get a handle on how the Markov chain behaves out of any given state now, say G prime, then all I have to do is I can embed G prime into, I find an embedding, which I know exists, into this random G, and then that embedding induces a projection to some random graph just by taking whatever this injection is. I take out the corresponding random graph, and that gives me then a pair of graphs G. I guess this should be G prime. It should be G prime. So this gives me a pair of graphs G prime and gamma prime. G prime I fixed ahead of time, and so there's a little bit more work to be done, but the idea is that now this is no longer exchangeable. G prime was fixed, but the distribution of gamma prime depends. This is another one. So this should be G prime, just like down here. And so this operation here is really these pair of W's is effectively doing, right? It's effectively picking out an injection and taking the corresponding component of this random graph over here, in essence.
Due to your relative exchangeability, if you look at this little piece in your graph G, not the Erdos-Renyi one, the one which is your first graph, then that you can find sort of this in the Erdos-Renyi graph, and the labelings don't matter because you have this conditioning on the subgraph exchangeability, and therefore you can sort of generate.
Yeah, that's right. And so this idea, which works out nicely and is relatively straightforward in the case of graphs, it extends this technique which I developed for this problem. It actually generalizes to somewhat arbitrary combinatorial structures, which I don't necessarily.
Again, there must be some notion of density, which is implicit in the ones it's extending to, or not. Some density.
Yes, and in a very clear way, actually. So I could tell you that afterwards, because it does depend on that very much so. So I said there were conditions on the graph G, and I think it will have to be dense, at least in order for our proof to carry through. But there's also counterexamples for why, it's not so easy to maybe extend. Although, we're not sure where to go. We tried. Okay. Now, in the continuous time case, the behavior can be a bit more interesting. So in continuous time, we have an uncountable collection of time points. The state space of infinite graphs is an uncountable state space. So we can have possibly infinitely many jumps in bounded time intervals. Okay, and so whereas we can't have certain types of behaviors in discrete time, we can only have this kind of jump where I've run it through this dense kind of operator, right? But in continuous time, the kinds of jump behavior that I can see, and I should say this is actually a bit weaker, a bit more general. I'm not assuming projectivity in this theorem, just CAD-lag sample paths, which just means that the projections stay where they are for a positive amount of time. So there I can't explicitly characterize the transition measure, but we can characterize the discontinuity types into three types. There's either a global kind of jump, which just means that at the time of a discontinuity, a positive fraction of edges changes status. Or we might have a single vertex jump, which means at the time of a jump, a single vertex is chosen, and only edges incident to that vertex are allowed to change. Everything else stays fixed. Or a single edge flip, which a single edge is chosen and it switches. Everything else stays fixed. Okay. And so this is just a description of the discontinuities. If we add back in the projectivity condition, then these discontinuities can be characterized by some unique measure. Okay, so we get what's ordinarily called in this combinatorial process literature a Levi-Ito-Khinchin type representation. This is an analogy to the Levi-Ito-Khinchin representation for Levi processes. Okay, where there's some breakdown, some similar breakdown, analogous breakdown in terms of discrete and continuous components. So a Levi process can be decomposed into a Brownian motion, a Poisson process, or a compound Poisson process, and a pure jump martingale. And there's some analogy to that here. Although everything's combinatorial here, so everything is in some sense discrete. Okay, and here I just want to point out an analogy to, or really an interesting, I think, observation or consequence of exchangeability, which we saw here that we can we decompose the jump behavior into three different types. There's some global, some vertex type, and some edge type jump. The Aldous-Hoover theorem also has that same kind of decomposition. I've observed this in a characterization of edge exchangeable networks where there's the same breakdown analogous to these three types for the different types of edges that come up in those networks. And in the GraphX models, which were mentioned yesterday, Christian talked about the stars and the isolated edges, and then there's more I guess global types of edge types in the GraphX models. And I think that the commonality of these properties is really a consequence. This is a consequence of exchangeability. That's at the end of the day. So that's just merely an observation.
Wait, what are the three things in Aldous-Hoover? I don't understand.
Well, okay. So if you look at this breakdown here, okay, this.
Saying the sites and the edges.
So this piece here is every edge is affected by this random bit. This is a globe.
You have that there in addition, right? The first one is just picking out the ergodic components in Aldous.
Mm-hmm.
So that's of different type, because otherwise you would have four types in Weierstrass. Because in Weierstrass you have the edges, you have the stars, and you have sort of the graphon edges. And in addition, you have the ergodic component, so that would be four.
Well, this is an analogy, I should say. I mean, I don't know what more to say than that. There's something that is, in some sense, affects everybody in the graph. And if I'm thinking about the first type of edge in the graph X is one that is, these are edges that occur infinitely often, right? Or that are somehow connected to a large component of the vertices. I don't know much about. I don't know all of the details of that, but this is maybe an observation.
Ergodic component somewhere in your theorem also? Is
That doesn't come up, no.
So everything is ergodic, or it's not ergodic? Or
No, okay, the jumps, okay, so maybe this gets to something that's kind of hidden, which is that these type 2 and type 3 jumps are ergodic. The type 1 jumps may not be. So if I maybe could extract that out if I wanted to. You know, these are being generated at each time according to an exchangeable measure or exchangeable measure on these pairs of graphs. So okay, so maybe I should be writing 4 components. So, okay, good. Okay.
Harry,
Yeah.
you go back a slide. With this in view, that makes me wonder whether maybe I missed something about the discrete time one. Can I think about the discrete time one as, is this fair? Like I could have a Markov process which is evolving the ergodic component, the first, you know, C naught or C empty set, and then also Markov chains for every row, every column, and every edge. And then can I then understand the Markov transition as acting per edge, and then also being allowed to depend on its previous history? Is that the same description?
Well, I don't know, as you've said. I've thought about this kind of thing as well. I could say I think that you could make that description in some way, in some case, but I don't think it's as general as you're saying. I mean, so in discrete time, you can't have just one edge change in going from t to t plus 1, right? So I don't know if that would be possible in what you're talking about, but
I don't think it would, because if there were positive measure event, there'd be a countable number of them, so you get a positive.
Right. So I don't know if I tried to work this out at one point, but I don't know if it was. I wasn't getting anything interesting, but we could talk about it again. Yeah, thanks. Okay. Now this is so that's really the main component. This is the main this and the previous theorems on graph valued processes. But here I have some other more recent work on more general spaces, and I think this is actually something when we specialize it to graphs or really any type of combinatorial time varying data set in a combinatorial space. These might be the most readily applicable in practice, I suppose, and I'll explain why I think that in a few pages here. But this is the idea of what I call a combinatorial Lévy process. So I mentioned Lévy process is the classical version of a Lévy process, or a real valued Lévy process, which is a process with stationary independent increments and Cadillac sample paths. Okay, so there the increments are defined. If I have a real valued process, increment between time t and s is the difference between the process at time t and the process at time s. Here I'm talking about combinatorial processes, so I want to define the increment as a combinatorially. Okay, so I want to encode some kind of increment in this way. So, and the way that I'm doing it on the space of graphs. So a graph is just a set. It's a set of edges, right, on some base set. Okay, so the increment I'm going to define is just the symmetric difference on the edges, or another graph which encodes those edges at which the two graphs differ, right? So between 1 and 2, there's an edge. There's no edge here. There's an edge, so there's a difference, and we put an edge there. Between 2 and 3, there's an edge in both, so there's no edge in the difference. Okay. So this is what I'm defining as an increment, and then a process, a graph-valued process. I'll call it a Lévy process if it has stationary and independent increments with respect to this increment operator. And now in this case, I'm back in the, I am closer to,
Are the graphs labeled or unlabeled?
they're labeled.
So I should just think of it, but you have more than just a set of edges because you know when two edges are incident. So I should really think of it. I have the natural numbers and then I have pairs of them and that labels, and then any subset of that is a graph finally. And then the increment is your symmetric difference.
I have this, I mean, this, I don't understand. This is
I
a
just
graph.
don't understand the sigma algebra on your graph, so that's why I...
Oh, the sigma algebra I'm dealing with is just is a very it's the one that's generated by the projections. Okay, the product discrete topology, right? Okay, so here I can standardize this to assume it starts at the empty graph. That won't matter, and then I define the increments properties as usual, except not as usual because it's with respect to this combinatorial increment property. So now when I say this, when I'm describing the increments, I'm talking about random graphs again. So this keeps everything. I guess the nice thing about this is that the process evolves on the space of graphs, and the increments are also random graphs, so everything is discussed in terms of graphs, as opposed to the previous processes where I had to go into a different space, these paragraphs, which can be a bit cumbersome maybe. So in this case, we also get a characterization. It's
We're not done with your definition. So you have this and then the independent increments.
okay. So
They're
and
independent,
that
yeah.
comes
so I have a stationary increments, which means that the distribution of the increment between any two times only depends on the difference in the times. And the independence property just means that if I have non-overlapping intervals of time, then the increments on those intervals are independent. Okay, and then CAD-lag again just means that
they're all allowed to overlap even at the end. So just shouldn't really overlap.
there's no overlap.
No, it's strictly left.
T1, T0, well, does it start then with T2, the next one, or is it gamma of T1, T2?
It would be gamma T2, T1.
So then the two
Oh, did I leave something
the
out?
intervals so are you talking about the first and second interval, they interlap, they
They
intersect
overlap.
at-
I think I can allow them to overlap at the endpoint. That's fine. Sure.
That's what
Yeah. Okay. Thank you. Yeah. Okay. So in this case, we get another type of representation in terms of now the measure is unique for the process, and it's on the space of graphs, and it's just defined in terms of the increments. So the infinitesimal jump probabilities are defined in terms of evaluating this measure at the increment between these two, the two graphs that we're talking about. The thing that also is maybe good about these processes is that this theorem is true. This is true in the absence of exchangeability and also when the state space is finite. So the previous the earlier process I was talking about depended on both of those assumptions. We needed exchangeability, and we also needed the the graphs to have infinitely many vertices, but we don't need that in this case. And this is maybe why I think that it has better potential in application, because I mean, as a very naive or crude way to perhaps estimate this transition measure, well, this is just an empirical measure, but this is something that we can actually do in this case because we actually observe the increments, and the increments determine the distribution of the process, whereas in the earlier, in the general graph valued processes, these aren't defined in terms of the increments, and we don't observe all of the information in the transition operator, right? Because we have a pair of graphs and we only see kind of some kind of shadow of where the previous state hits that operator. Right, and these are also not confined, these processes weren't, I didn't originally define them on the space of graphs. They can be defined in arbitrary kinds of combinatorial spaces. As a simple example, we could have, in addition to edges, we could have a set, so a special set of vertices. And these are just now pairs of sets, symmetric difference, operates the same way. The assumptions operate the same way. And there was some, I think that it's late enough in the day that I should stop here. There was some related work, but it's extended to more general structures. It's not specific to graphs or networks, but this is work that takes the idea of relative exchangeability and the characterization of these graph-valued processes to a general class of combinatorial spaces. So this is work I did with Henry Tausner. He's a logician at the University of Pennsylvania. So there's some interesting notions from model theory that come up to actually help us in those proofs. And actually those ideas from model theory, that the properties that I need my graph to satisfy in my theorem are just a very special case of those. So that actually explains perhaps why all of this works. But the main references on the networks, the network models, can be found here. And I think I'll stop. Thanks. Yeah.
Am I right in interpreting that both the earlier processes, so exchangeability and projectivity, and also the independent increments, rule out mechanisms, dynamic mechanisms like preferential attachment and transitive closure?
Most likely preferential attachment, yes. What's transitive closure? I'm not sure what you mean.
Friends of friends becoming friends. So a certain probability that if you've got a two-path between you, that there will be a direct edge.
Yeah, I don't think you're allowed. You're not allowed to take that into account. Yeah. So it is a very localized thing. Yeah. Yeah.
Although you do have these neighborhoods. So in your thing where you have neighborhoods A, you might be able to enhance the closing of triangles by having using those A's that you just.
You're saying in this case, in this more general case.
In this case, exactly.
Perhaps, yeah.
You might be able to put that in and do triangle, an enhanced triangle.
If you've got a prior definition of your communities.
Yes.
But not communities that are defined by the process itself.
No, XG is the state.
No. I think the answer is no.
Yeah, perhaps I've gotten confused. I thought it was actually the other way around. That if the communities are exogenous, then you no longer have exchangeability. But if they're endogenous, then I think it's as with the I guess with the Graph-1 models, you have kind of a latent variable that can use to model that, but not exogenous communities, because I would think that would break exchangeability. Like for example, if we wanted to have, I don't know, male and female groups, which we know that means you can't have exchangeability anymore. Is that accurate, or am I misunderstanding, or have I gotten myself confused?
So male and female groups encoded as latent or as encoded in the process?
So I guess that's what I'm trying to figure out.
So,
Not red.
so I mean, I think that.
You would say all even are male, all odd are female.
Well, then it's now the process itself wouldn't be exchanged.
The xi I, you could have the xi I smaller than 1/2 being male and xi I larger than 1/2 being female, and then you would have the endogenous definition, but still it would be.
Yeah, well, that is, in some way then you're treating the assignment as random.
Yeah,
in some sense.
yeah, exactly.
Yeah, that would happen. Although I dispute whether that actually counts as.
Oh yeah. Okay.
But yeah.
That's what I'm trying to figure out. Is it, I guess, can one then, I mean, obviously it's something you would actually observe if you were to try to put this to data. So, so the question is, how would you include that in whatever?
Our gender is determined by chance, randomly, at our inception.
Right.
Conception, sorry.
So I mean, I think that, I mean, the way that you might see it is in the same way as if you were to fit. So this Graph-1 that is just this block diagonal Graph-1 that's often shown for the stochastic block model. I mean, you would pick it up in the same way, perhaps. But I mean, but I don't know exactly. If you wanted to encode it as strict as fixed, then that can't be done in the original process. Perhaps in these later ones, right? Like you said. Yeah.
So in the original Definetti, you could sort of determine the probability p as the limit of densities. So is there some way we can actually identify what you get out here in the limit? I mean, so it raises sort of this question of identifiability and whether you can actually.
Well, very likely there is an issue of identifiability for this, not this, this measure here, right? In the same way that you would have it, because there is, an ergodic or not a non-ergodic component, this random piece. Yeah, that's right. So I think you'd have an issue. I haven't thought about estimation, though. So.
Can we actually sort of characterize it, right? Because if we want to think of estimation, we want to come up with equivalence classes for identifiability, and then we would output a member of the equivalence class that you would want to study sort of what the equivalence classes are.
Well, I think the equivalence classes are determined by whatever the equivalence classes of Aldous Hoover is, because in the proof, in the proof, the only way that this thing comes up, that this ergodicity issue comes up is, the Aldous Hoover theorem. This really builds off of the Aldous Hoover theorem. So whatever you know about that perhaps is helpful. But no, I haven't thought of any estimation or anything. I'm hopeful that maybe somebody would find something interesting here. I don't know.
Looking at the time and at the faces, I think let's thank Harry again and all of you.
Thank you.